Welcome to this video where we continue to talk about content in the book Introduction to Nonlinear Control. And in particular, in this video, we are going to cover content in chapter 9 and talk a bit about control Lyapunov functions. So what we've seen so far in terms of Lyapunov functions were Lyapunov functions characterizing asymptotic stability of dynamical systems of the form x dot is equal to f of x. So systems without input, we have x dot is equal to f of x. Without loss of generality, we have assumed that the origin is an equilibrium. And then a Lyapunov function is a function v, which is continuously differentiable. And additionally, we need two k-infinity functions and a positive definite function to ensure that these two conditions here are satisfied. First one simply means that the function v is radially unbounded, and the second one means that the time derivative of the function v along solutions is strictly decreasing until the origin is reached, and that then implies global asymptotic stability in this case. Okay, so now we want to talk about control Lyapunov functions, meaning we are going to look at systems of the form x dot is equal to fxu, where we now have an input which we want to design in a particular way, namely to also have an asymptotically stable origin. So we want a stabilizing controller stabilizing the origin of this system with input. So general approach here would be to use a state feedback, so to define u is equal to k of x, unknown function k. And then we can actually go back to our setting of Lyapunov functions, namely if we set in plug in the definition of u is equal to kx in our degrees condition here. And then f of x comma kx only depends on x, not on u anymore. So if we can find a k such that the degrees condition here holds, then v is a Lyapunov function for the closed loop system. So here there is not much new yet, but what we can also do is to not define a feedback law u is equal to kx directly and simply state this degrees condition in terms of the function where we have not selected a feedback law u yet, and then we want to guarantee the condition that whenever we take an x unequal to 0, that we can find an input u such that the degrees condition here is satisfied. And if we can guarantee that condition, well, then that gives us the definition of a control Lyapunov function. So here we more or less copy the same definition as for Lyapunov functions. So we still need k-infinity functions, we still need our continuously differentiable function v, but now we focus on the system with input. We have our radially unboundedness condition, and we still want the degrees condition to be satisfied, and we can state it in the way that we want that for all x unequal to 0, there needs to exist an input u such that the degrees condition is satisfied. Well, yeah, so with the slight variation of the Lyapunov function definition, we obtain a control Lyapunov function. And that control Lyapunov function then, of course, again allows us to conclude asymptotic stability under an appropriate selection of the input u. But that also then leads us to the first question that needs to be answered in this context. So if we know a control Lyapunov function v, what is a good way, or what is a common way in the literature to define a corresponding feedback law? So let's get started. So we assume that we know a control Lyapunov function. Additionally, here we focus on a specific form of a dynamical system. Namely, we assume that we have a control affine system, meaning our right-hand side can be written in this way, meaning we have a term only depending on x, and then we have a term linearly multiplied with the input u. And for simplicity here, we assume that u is one-dimensional, but this can be extended also to multi-input systems. And just to keep in mind what control Lyapunov function means now, well, we know by assumption that this condition here is satisfied for the function v. A different way this is often presented in the literature is by using the so-called Lie derivative, LFV or LGV, which simply means these inner products here, the components of the inner products, and this representation is only possible for control affine systems, but not for more general systems. So that's why we've assumed that here. And then this decrease condition here can be characterized in an equivalent form, also often found in the literature, so there is no need to rewrite it, but just that you see also an alternative formulation depending on the book you look at or the paper you look at. The decrease condition up here can be written in terms of the equivalent condition here, saying that whenever LGV is equal to 0, then the condition LFV needs less than 0 needs to be satisfied if x is unequal to 0. How do we see that this condition is needed? Well, if we assume that LGV is 0, this simply means that this term up here disappears, meaning we are losing the degree of freedom in the input u to guarantee that the inequality here is satisfied, meaning this term here needs to be less than 0, and that's captured through this condition here. On the other hand, if LGV is unequal to 0, well, then we can always select u large enough, just then also depending on the sign, such that this inequality here is satisfied. Okay, so whichever representation you choose, so this representation or the representation through the Lie derivatives, there is then one particular controller design you find in the literature, namely defining k of x in this particular way here. And looks complicated, but yeah, you don't have to keep that in mind, and you can simply look it up whenever you need it. And you find it in several books with corresponding properties of this feedback law. Namely, this feedback law guarantees asymptotic stability of the origin of the closed loop system. The feedback law inherits all the regularity properties of the control Lyapunov function, except for the origin, meaning if the function v is twice continuously differentiable, 3 times continuously differentiable, then the similar statements can be made about k of x, again, except for the origin. And if an additional property is satisfied, this so-called small control property, which means that if x is going to 0, then also the k of x has to go to 0, then we can also make a statement about the continuity properties at the origin. Well, how do you find this feedback law in the literature? So it's known under the name universal formula or Sontag's formula, going back to Eduardo Sontag, who proposed this particular feedback law in one of his papers. Okay, so this answers one question, or kind of we started with what is the definition of a control Lyapunov function and what does it tell us? It tells us that there exists an input asymptotically stabilizing the origin. How do we find such a feedback law? Well, we can use this particular formula shown here on this slide. And the next question would be, but how do we find a control Lyapunov function? And unfortunately, as it is with nonlinear dynamical systems, when you want to show asymptotic stability, there is no straightforward way to do that. So finding a Lyapunov function is kind of an art and you need experience. Similarly, finding a control Lyapunov function is not straightforward, and only for particular classes of systems there are constructive methods to come up with a control Lyapunov function. At least if we are not satisfied with just local properties which you might get from linearization. Okay, so for which classes of systems is there a constructive method to find control Lyapunov functions? That's the case for so-called systems in strict feedback form, where we can use backstepping. What is a system in strict feedback form? Well, it's a system with this particular structure here, where we start with x1 dot, and that's then a function just of x1 and x2. x2 dot is a function of x1, x2, and x3, and we can continue until xn dot, and that's where then also input u appears in the right hand side. Graphical representation is also shown here on the right of these systems in strict feedback form. And as a simple example, we can look at this two-dimensional system here, where x corresponds to x1 in the expression above, and psi corresponds to x2, where we then see, well, that in x2, or for x2 dot, the input appears in the right hand side. Okay, so this is a very simple example, and here I'll give the idea how you can construct a control Lyapunov function for a system like that through backstepping. It is worth it to look at a more complicated dynamical system. So state x of dimension 3, for example, or higher, and then go through these calculations once by hand to familiarize yourself with these steps. But here, what we are going to first focus on is this first component of the dynamical system, where we now have x as is one-dimensional, and we assume for the moment that psi is the input. If that's the case, then a construction of a controller and the corresponding control Lyapunov function stabilizing the origin of this one-dimensional system here is not too difficult. So we would, as a first step, take psi as an input, define a corresponding feedback law and a corresponding control Lyapunov function. However, then we need to correct the mistake of taking psi as an input, because we cannot freely design psi, and we have to treat it as a state. So that's why we introduce as a next step an error variable, the mismatch between xi and what we would like xi to be. We define that as z. Based on z, we can define the error dynamics, taking the derivative and then taking the derivative of xi here or here. This is where then the input u pops up for the second order system. For higher order systems, we would need additional steps, but in this case, we would now have the input u appear in the aerodynamics, which means we can define a stabilizing controller for now the aerodynamics, which can depend on x and z, and we can define a corresponding control Lyapunov function depending on z. And then as a last step, we can define a control Lyapunov function for the overall system here by combining the function v1 and v2. And now this would be a control Lyapunov functions in the variables x and z, but z can be replaced through psi again through this coordinate transformation here on the left. So I hope the idea, I could convey the idea here of backstepping, but as I've said, it is worth it to go through these steps by hand yourself to practice it. And this concludes kind of the three steps of this presentation. What is a control Lyapunov function? How do we define a controller if we have a control Lyapunov function? And under specific assumptions on the dynamical system, how do we find a control Lyapunov function? With this, we conclude the presentation here and continue in the next one with sliding mode controllers.